Welcome to this morning's session on modern security best practices for microservices. My name is Seth. I'm a developer advocate at Google. Prior to that, I was a developer advocate and software engineer at a company called HashiCorp. Prior to that, I worked at Chef Software. And then I did other stuff before that that's not really relevant. One of the things that I like to mention is that I don't have a traditional security engineering background. I went to school for computer science. I have a computer science degree, but I'm not a security person. I don't have any white papers published. I didn't spend years doing a PhD in security. Instead, I've spent the last 7 to 8 years really focusing on practical security. And that's going to become really important throughout this talk. It's been my goal for the past 7 to 8 years to prove to people that security doesn't have to be hard, that you don't need a doctoral degree or a master's degree in cryptography to be able to do security well. And that's really the goal of this talk, is to convince all of you that as well, while also talking about microservices. So before we talk about microservices security, let's talk about traditional security. I think this picture best represents traditional security. We just put a padlock around it, and it's secure. There's absolutely no way anyone could press the K or L or semicolon key on this keyboard, because there's a padlock in front of it. It has to be secure, right? Unfortunately, this is the way we tend to think about security. It's a binary operation. It is secure or it is insecure. Instead, we have to think about security as a scale, where things go from the most secure to the least secure. So we have to stop thinking about security like this. But why? Why have we traditionally thought of security as a big padlock around a keyboard? Well, when we look at a traditional application architecture, it looks something like this. You have a top-level load balancer. That's probably a hardware-based load balancer, maybe something like an F5, that hits your physical data center, where you own the brick and mortar and the servers that are inside of it. That hits a firewall that also might be some physical firewall appliance that you purchased from a vendor, like a Barracuda, et cetera. And then after that firewall, we are in the secure zone, or the DMZ, if you will. And within that secure zone, there's one huge monolithic application and one huge monolithic database. You'll notice that within this application, there's no inter-process communications, right? This is just a system call to my internal library. I'm not reaching out to other services. I'm not reaching out to the public internet. If I want to talk to my order service, it's inside of the same application. Similarly, my database is co-located in the same secure zone as my application. So I'm not going over the network. I'm not worried about authenticating those calls. And in this model, where we have one load balancer, one firewall, and one secure zone, the idea that we can wrap our applications in a padlock makes a lot of sense. That firewall there is the gatekeeper. Anything that goes in and out of that firewall is secured or not secured as dictated by our security team. And if you have this architecture, it makes sense to continue behaving this way. One thing that's important to note is that that firewall is often managed by one team who has all the context of the security of your organization. So the security team is managing the threat model and has a good understanding of all the requests. If you want a port opened or you want a protocol allowed or disallowed, you have to file a ticket. And that team maintains kind of the history of all of those changes, as well as what's allowed and what's not allowed. But we know that there's a lot of problems with this approach, right? One of the main problems is that we can only deploy this application once a year, because that's how long it takes everyone to get their changes in, and it's difficult, and you have to collaborate across all these different teams that are working on different parts of the project. And that database doesn't really scale very well. We have DBAs who are constantly repairing it. And we really can't leverage other external services because everything's contained within this one little secure zone. And for this reason, we tend to adopt microservices. There's a lot of advantages of adopting microservices. They come with drawbacks at the same time. My goal is not to convince you to adopt microservices. It's more just to show you how security changes if you do. So this is a traditional architecture. This is a microservices architecture. The first thing you'll notice is that we still have a load balancer, but that load balancer is probably not a hardware-based load balancer that you bought. Instead, this is most likely a software-provided load balancer by maybe a cloud provider or something that exists at the software layer. On top of that, we have firewall rules instead of a physical firewall device. Instead of one secure zone, we have multiple subnetworks. Each of those networks have applications that must communicate within that network. And then we also have network-to-network communication. So I might have my front-end service and my back-end service and my order service and my search service, and they live in different zones and different regions for availability. In this model, I have to worry about service-to-service communication. How do I secure that? I need to think about things like TLS and managing PKI infrastructure. Similarly, we also have managed services that come into the mix. Many cloud providers offer things like hosted databases or hosted caching services. So instead of managing our own database and worrying about scale and hiring DBAs, we can offload that to a third-party provider. But that often means that we need to do that over a public internet connection, or we have to do some type of VPN or type of peering operation in order to manage those connections. Where this gets really complicated is that the teams that are managing these connections are not just one team. In the traditional architecture, we had the security team that managed the firewall. Now, we have the security team managing the firewall rules. Each individual application team kind of manages their own network stack and their own application stack. The interns manage this stack over here, and then Chris manages those managed services. How many people have Chris in their organization? Yeah, you know what I'm talking about. This is the reality of microservices. A lot of this happens because we're trying to break apart a monolith. A lot of this happens because we're in a small startup and we're trying to move quickly. But this is, I think, in my opinion, a very accurate description of what a lot of microservices architectures look like. The problem is that security exists at every phase. Earlier, I said that security is not a binary operation. Something is not secure or insecure. Instead, it's a sliding scale. We have different layers of security here. We have security, our load balancer layer. Perhaps we want to block an entire country from accessing our service because of import-export laws. Then we have our firewall, which can do things like IP rate limiting for us. Then we have service-to-service communication, which might be secured via mutual TLS. And then we have user authentication on top of this, which might be built on something like OAuth, et cetera. It's not a binary operation. So we have to stop thinking about security as this thing that you put a padlock on. That's not how security works. You can't just say this is secure or this is insecure. Instead, we have to start thinking about things like probability and a range. How secure is this? What is the probability? So the same way we start thinking about availability. Do you have 3 nines or 4 nines or 5 nines of availability? That's how I think we should talk about security too. This has 5 nines of security. This has 1 9 of security. And it doesn't map one-to-one, but it gets us thinking that security is not a binary operation. So in order to think about security and the way I think we think about security, we actually have to go back in time. I think the best example of how we should be treating our applications today comes from the 16th century, when people were designing castles. Castles are not designed with binary security in mind. If a castle or a fort had binary security, there would be a moat around the outside. That's it. And if you cross the moat, you were screwed. Right? If your enemy is across the moat, you were screwed. We do that to our applications today, though. We wrap it in a firewall, and we say, well, if you're in the firewall, everything has to be good to go. Instead, we need to start structuring our applications like this, where there's multiple layers of security, where just because you cross the moat doesn't mean you can make it to the king or the queen's lair and cause an assassination or an internal coup. Right? It gets more and more difficult the closer you get to sensitive and important data. So what are some concrete action items here? Well, I think that cloud providers created a double-edged sword here. The reason a lot of people are adopting microservices is because of things like managed services, like managed databases and managed caching, because all of the cloud providers are pushing it, partially because it causes you to spend more money. And I say that as I work for a cloud provider. But I also think on the flip side, it helps. I think there's a really good benefit. Every major cloud provider has dedicated teams of security researchers who are thinking about security in ways that you couldn't possibly imagine. Things like the Spectre vulnerability, where a fundamental flaw in a CPU architecture made an application vulnerable, right? If you're a Node developer or a Ruby developer or even a C developer, these aren't things you think about every day, right? You kind of inherently trust that your CPU is not going to be the vulnerability vector for an attacker. And there's a famous quote that's been misattributed a bunch of times, but it's, if security is someone's part-time job, are you as good as someone else who it's their full-time job? And all of these cloud providers have public bounty programs, et cetera, where they're thinking about security very differently than you think about security. You're thinking about that one person who's trying to misuse your service. They're thinking about very low-level attacks, hardware-level attacks, infrastructure-level attacks, et cetera. At Google, we have a thing called Project Zero. You might have heard of it. We pay millions of dollars a year in bug bounties to people who find bugs in our software and bugs in open source software. Additionally, cloud providers have really cool physical security. If you've ever seen a movie like Mission Impossible or like a James Bond movie where there's a museum heist and there's like laser beams and like that kind of stuff, that actually exists in real life. I've been inside a Google data center before. We have these things. Sorry, I don't know why my slide went ahead. So things like laser beam intrusion detection system, that's a real thing. It doesn't just exist in movies. Things like dual biometric authentication, both iris scanners and thumbprints to authenticate people. Cloud providers take security very seriously. Again, this goes back to like threat models that you're not even thinking about. Right? As an application developer or an infrastructure engineer, you're thinking about your domain. But what happens if someone has physical access to your machine? How can we prevent that? And once it happens, how can we detect it and mitigate it? So speaking of that, things like hardware security. At Google, we manufacture almost all of our own hardware so that we don't have bugs in the supply chain. We manufacture our own ID cards so that we don't have bugs in the supply chain. Right? These are things that you generally don't think about. Just like if you buy your company ID badges from a vendor, how can you trust that vendor to not make that same ID badge for a competitor or a government agency? Additionally, we have things like secure boot, et cetera, that make it really, really difficult for people to tamper with these systems. Another thing I always like to mention is automated vulnerability scanning. There's a lot of companies out there and a lot of open source tools out there that are doing this as a service. If you are writing software in a language that has a vast ecosystem, Ruby, Python, Node.js, of libraries and dependencies, it's very easy to get caught up in a world where you have a dependency of a dependency of a dependency of a dependency that has a vulnerability. And as that fans out, it's really difficult as a human to reason about that. So we have to leverage things like automated vulnerability scanning to tell us, hey, there's a package that's outdated, or hey, there's a package with a security vulnerability, here's a fix for it. GitHub has been rolling out these types of functionality. There's, again, open source projects and paid projects that are doing this for you. This is definitely something we can do at the software layer to help increase our security. So what does quote-unquote modern security look like? Well, I already said if you're doing the traditional architecture, you can still wrap things in a firewall. It tends to work pretty well. But if you're in this microservices world, and you're trying to be modern, and you're trying to be hip, and you're trying to be as secure as possible, what are kind of the high-level features that you should have? The first one is really straightforward and obvious. It's just encryption everywhere. We want encryption at rest, meaning when the data is persisted on disk or a file system or in some object store, that data should be encrypted. We should be rotating those keys regularly. We should be using the latest and greatest encryption algorithms. Additionally, we want encryption in transit. As we are moving data between services or between our users, we should make sure that we are using TLS and that we're not using a deprecated cipher suite and that we're not using a known vulnerable version of OpenSSL, unless you work for the US government, in which case you have to because they haven't approved the latest version. The next functionality is dynamic, time-based, and revokable credentials. And this is where I start throwing a wrench in how people think about security. Today, how many people work on an application that has to talk to a database? OK. How does your application get that database credential? So my guess is that if you work for a startup, you Google how to create MySQL user. You go to Stack Overflow. You copy and paste some stuff into the MySQL console. And then you have a user. And you put that username and password in a YAML file, and you check it into source control, and your app works. Congrats. If you work at like a larger company, like an enterprise, it's a little bit different. You file this thing called a Jira ticket. You wait 6 to 8 weeks for the DBAs to provision your account. Then you put it in the text file and commit it to source control, et cetera. Both of these patterns have a really difficult root of trust. In all of these scenarios, a human has seen those credentials. Multiple people know the username and password to the database. Additionally, that username and password is unlikely to change for the foreseeable future. Unless you work in a regulated industry, something that has PCI compliance or medical, things like HIPAA, PCI, FIPS 142 compliance, you're probably not rotating your credentials regularly. And that's because there's nothing forcing you to do that. Your app is working, everyone is happy. Why would you risk downtime by creating a new database user and hoping it has the same permissions, right? That's not a good use of your risk model. So I challenge that we have to think about security the same way we think about IP addresses. So bear with me here for a little bit. Let's forget about security. When you connected to this Wi-Fi network, your laptop or your mobile phone made a request, joined the network, and it was issued an IP address from the DHCP server, 1.2.3.4. Additionally, it had some metadata associated with that called a lease. And I think on this network, it's 8 hours, but that's configurable. What that means is your machine, your phone, your tablet, whatever, gets this IP address, 1.2.3.4, and the DHCP server says, you can have this for 8 hours. And at the end of 8 hours, you need to come back to me and say, hey, I'm still using that. And I'll tell you if you're allowed to keep using that IP address. So you go about your day or doing stuff. You close your laptop, you go to dinner. You come back. Your laptop says, hey, DHCP server, I was 1.2.3.4. I know my timer has expired. Can I still be 1.2.3.4? And the DHCP server says, yeah, you're good to go. You can have it for another 8 hours. Or the DHCP server comes back and says, no, I gave that to someone else. Here's a new IP address, 5.6.7.8. This is you from now on. That negotiation, and my oversimplification of that negotiation, happens behind the scenes without your knowledge pretty much every time your device connects to a network. How does this relate to security? Well, we actually should think about passwords and credentials and secrets that same way. So instead of a human logging into the MySQL or the Postgres console and creating a user and putting it in a text file, instead, at boot, our application should request a credential from MySQL or Postgres or our database server. And the database server should issue a unique credential, just like a DHCP server issues a unique IP address. And it should also issue a lease associated with that secret. So just like an IP address expires or must be renewed in a configurable amount of time, we want to create secrets that expire and need to be renewed within a configurable amount of time. This helps reduce what we call secret sprawl, which is where you just have hundreds of secrets all over the world. So instead, if we adopt the DHCP model, my app requests a database credential. A centralized service gives me back a database credential and says, you can use this for 24 hours. At the end of 24 hours, I request a new database credential. And now my app automatically restarts and loads those new credentials. That means every 24 hours, I'm getting a new username and a new password, and I'm reducing my surface area for an attack. But at the same time, I need to be able to revoke them early. And again, this is a functionality that happens at the DHCP layer as well. I can revoke all existing IP leases in a DHCP server. And I should be able to do the same thing for secrets management. If there's an accidental security breach or a rogue employee, I should be able to, like, one button, revoke all of the credentials, no matter how much time is left on their lease. And these are kind of the features, in my opinion, of modern security, is these ideas of dynamic, time-based, and revocable credentials. But all of this is really hard. Like, it's really hard to do this right. And going back to my earlier comment about I don't have a PhD in cryptography, and I come from a practical security background, it's unrealistic for every application developer and every infrastructure engineer to be good at security. And I don't think it's a requirement, and I think it's a bad practice. Instead, we should be taking the people who are good at security, the people who are thinking about these problems all the time. We should take what they know, and we should put it in an API and give that to people as a service. So if you're doing encryption in Node, or Ruby, or Python, or C, the way that you do that, the way that you do symmetric ciphertext encryption in every programming language is different. The cipher suites are different. So if you live in a polyglot organization, you have to decide, how am I going to encrypt these things? How am I going to do this? And you place the burden on the application developer, on the systems developer, to become an expert in security. This often leads to things like career stagnation or employees just flat out quit. Right? If I'm a Node developer or a Ruby developer, and I want to just write Ruby and I want to just write Node, I don't want a PhD in cryptography, and I shouldn't need one. I shouldn't need a PhD in security to be secure. So all of these things that I explained to you should be available from an API. So if I want to encrypt some data, I make an API call, the data is encrypted, and I get it back. If I want to generate one of those database credentials, I shouldn't have to learn to speak MySQL and Postgres and Oracle. I should just make an API call, and I should get the credential automatically. So it's important that we codify these best practices, and it's important that those best practices are defined by industry leaders who are well-respected in the space, the security space, but from an application perspective and from a systems perspective, it needs to be available just via an API call, preferably an HTTP API call. So it turns out that there already is a consistent and easy-to-use experience that doesn't require a PhD in crypto, and it's open source. So there's this really cool tool called HashiCorp Vault. It's written in Go. It's a single static Go binary, open source, that is designed to really solve all of these problems. It tries to be a single source of secrets. It does things like being a database credential broker. It does things like encryption as a service. And it does a few more things. But in the remaining time, instead of telling you about what it does, I figure that I'll just show you. So who's excited for live demos? All right. Da-da-da. All right, so the first thing I'm going to do here is I'm going to start a Vault server. I can do this by just running vault server-dev, a little bit bigger. This is going to start a local in-memory Vault server. That's done. That's how fast it is to get up and running with this thing. You can download it in Mac, Windows, Linux, various ARM distributions. So it's pretty easy to get started and learn about this thing. Play with it on your local laptop. You don't have to install any packages or config. It's just a single binary. You can actually throw it on your desktop and run it from there. So next, I'm going to kind of show you the natural evolution of Vault, if you will. The first thing I'm going to do is authenticate to Vault. Now, when I authenticate, I'm going to log in as the root user. And this is a live demo, and that's not a best practice. The root user is kind of like sudo on Linux, right? I can do anything. In reality, when a user authenticates to Vault, that authentication is usually delegated to something like LDAP or GitHub, Active Directory, et cetera. But for kind of the purposes of this demo, I'm just going to log in as the root user for now. So I'm logged in as the root user. I'm now sudo. I can do anything. Not best practices. Don't do what I do. And I'm going to create some users. So I'm creating 4 users in the system, Sally, Bobby, Chris, and Devin. Again, you could delegate this to LDAP or Active Directory or GitHub, or there's a bunch of different authentication methods that are built into the system. But we'll come back to this later. So what is Vault? Well, the first thing Vault is it's a static key value store, or KV store. You can think of it like encrypted Redis or encrypted memcached. I have some plain text data. I want Vault to store it. I give it to Vault in plain text. Vault encrypts it, stores it internally, encrypted. When I want it back, Vault authorizes that and gives me back the plain text. So what does that actually look like? Well, I can use the Vault KV CLI to put a secret named foo. And we'll say the Wi-Fi password is open because there is no Wi-Fi password for the Radisson. It's really secure. And great, I get back this kind of metadata here, when it was created, when it was deleted, if applicable, whether it's destroyed, and the version. And I can get the value. So I can run vault kv get secret / foo, and I get back the value as well as that metadata. I can put a new value. Oops. Alt KV put. And you can see that it's versioned. So this is now version 2. The old version is still available. If I just run -version equals 1, I'll get back the original version as well. And I can delete these as well. So vault KV delete, secret foo. And I can list my secrets as well. So that's it. So static key value store. How many people feel more secure? Right? There's like one person. And they only raised their hand because they weren't paying attention and they thought they had to raise their hand. I'm just kidding. So this is always an important concept that I like to bring up, which is that the security industry has trained us to believe that security has to be hard. Vault has been audited a number of times by an independent security auditing group, the NCC group, and it continues to pass with flying colors. This is secure, but we're trained to believe that security has to be hard. If it's not like base64 encoded and you don't have to like duct tape it to the back of your Tesla in order to decrypt it, it can't possibly be secure. And this is just fundamentally wrong. This goes back to my earlier crusade of convincing people that security doesn't have to be hard. This is secure. And you can do security without kind of engulfing yourself in cipher suites and decryption algorithms. So that's the KV store. You put data in, it stores it, you get data back. One of the questions I always get then is they're like, oh, this is great. I have like all my user passwords. Can I put those in Vault? Like, probably shouldn't, right? Vault is not a database, right? It's not a replacement for something MySQL or Postgres. And if you have some front-end facing application, you probably don't want users authenticating via Vault to that service. That could take up a lot of memory and kind of duplicating the purpose of a database. Also, you probably shouldn't store passwords anyway. You should be hashing them instead of storing them because you never need the plain text. They're like, OK, well, what if I have something like credit card numbers? And I usually say, like, can't you offload that to some type of authorized .NET or Stripe or some service? Like, OK, well, I have to do background checks. I need passport numbers and social security numbers. Like, I have to store those. How do I store those securely? How can I use Vault for that? Well, you don't want to store those in Vault, because then that means for every new user that signs up for your site, you have to create a new entry in Vault. And that means Vault scales linearly with the number of users on your site, which means you now have to scale the service linearly. Not exactly the best operations mode. Instead, we should use a database for what a database is good at, storing data. But we want to encrypt the social security number, the passport number, the credit card number before we put it in the database. So if an attacker or a rogue employee gains access to our database, all they see is the encrypted values. They don't actually get the plain text data. You'd need to use a decryption key to get that plain text data. With Vault, this is available via what we call the transit secrets engine. So I'm going to go ahead and enable that. And the transit secrets engine encrypts data in transit. So previously, I gave Vault some plain text data. Vault encrypted it and stored it locally. With transit, I'm going to give Vault plain text data. Vault's going to encrypt it and give me back the encrypted text. Doesn't store it. So in this model, when Vault is encrypting data, it only stores the encryption keys. It's not actually storing any of the data that it's encrypting. It's your responsibility to store that encrypted text or that cipher text, typically in a database, but it could be stored anywhere. So let me go ahead and create a key. So I'm going to create a key called myapp in the transit secrets engine. Myapp, which is the end of that URL path there, is kind of like a symlink or a pointer to an encryption key, right? Because the encryption key is a bunch of random bytes. So I have to refer to it by something meaningful, and in this case, I've called it myapp. So let's say I have something like a credit card number or a social security number, passport number, and I want to encrypt that so that I can store it safely in my database. Well, I can do that by running vault write transit encrypt, the name of the key that I'm using for encryption, which is myapp, and I'll give it the plain text data. That's not my passport number, mostly because I just mashed keys. But if I do this, this will actually fail. I have to base64 encode this data. 64. And the reason I have to base 64 encode the data is because there's no requirement that this data is plain text. This could be like a PDF or a Word document or something like that. Which brings up an important point. You're probably thinking to yourself, well, this is great, but how the heck is my application going to run the Vault CLI? Like, I'm not going to install the Vault CLI and then shell out to do this encryption. Well, everything that I'm doing via the Vault CLI, and when I say everything, I mean literally everything, is available via the HTTP API as well. In fact, there's nothing that the CLI can do that the API cannot do. And that's because the CLI is just a thin wrapper around the actual HTTP API. So all of these Vault calls are also available via a JSON REST API. So you don't have to shell out to Vault CLI. If you're working in a programming language that can make HTTP calls, you can interact with Vault directly like this. That's also the reason you have to base 64 encode this data, because again, it's transmitted over a JSON payload under the hood. And if that was a Word document, one of the safest ways to transport a binary piece of data is to base 64 encode it as part of a JSON payload. So I take this ciphertext here, and I copied it to my clipboard, aka I stored it in my database. And 6 months go by, and now I need that passport number. I have to validate this person's identity. They're applying for a visa. I don't know. How do I get the plain text back? Remember, Vault didn't store it. I stored it. So I do a database lookup. I get that the ciphertext string. And then I ask Vault to decrypt it. And I say, hey, Vault, can you decrypt using the my app key, because we use the same key, this ciphertext? I pull that from my database. Vault gives me back, again, the base 64 encoded plain text. And if we decode this, we'll get back kind of the original value here. It's important to note that if I had 100 million database records, Vault would only be managing 1 or 2 encryption keys. So this is incredibly scalable, as opposed to the KV store, which has to scale linearly with each new record. Additionally, my app is not just one encryption key. It's actually an encryption key ring. So I can do things like rotate that key, upgrade that key, downgrade that key, etc. So if I were to do that right now, I can say transit keys, my app, rotate. That generated a new encryption key version. All new data will be encrypted with that new version. Old data can still be decrypted with the old version. And you can rotate those over time. This allows you to say to like a compliance officer, hey, all of our encryption keys are 30 days old or newer. We rotate them every 30 days. And you can continuously re-encrypt that data over time. So that's key value, and that's transit. So we have, here's some data, please encrypt it and make it secure for me. We have some transit, which is here's some data, please encrypt it and give it back to me. But what about the database use case that I talked about earlier? I have an application that needs to talk to a database. And the traditional model of a human creating that credential lacks what we call provenance, or a one-to-one mapping between the database credential and the person or thing using it. If I make a database credential, I log into the MySQL or Postgres console, I run create user, I get back the username and the password, and I put that in a YAML file. Now both the application and the operator that created that credential have seen the value. And I could have put that in my 1Password, or I could put that in a text file somewhere. So on the flip side, when we're looking at our logging and monitoring, and we see that that credential has been compromised, we have some anomaly detection, or our MySQL logs say, hey, this credential is misbehaving. It's making 100,000 queries per second, and that's abnormal. We actually can't say for certain which was compromised. Is it the application, or was it the human or humans that had access to that application credential? Similarly, if we have a front-end application that is multi-scalar, meaning we run 10 or 20 instances of it, or it auto-scales in some type of auto-scaling group, we don't know which one of those front-end applications was compromised if they're all sharing a credential. How do we know which one was compromised? Was it just a misconfiguration, or do we have a particular region that's been compromised? Instead, applications and services need to authenticate themselves and request their own credentials so that they, and only they, are the only thing that has ever seen that credential. Then, when we're looking at anomaly detection, we know for certain that this instance of this front-end application in this auto-scaling group was compromised. And that can really help with debugging and doing a security threat model. So what does that look like? Well, first I have to start Postgres, because I'm using Postgres for my demo, but it supports a number of databases. And then I'm going to enable the secrets engine called database. Secrets enable database. And I suck at typing, so I have a script here called configure database, which I will walk through with you. There's some bash stuff at the top. You could ignore that. Then there's two important pieces of data here. The first piece, which is this vault write database config, this is just configuring the database. So the way this works at a high level is I give Vault a very privileged credential, something that has the superset of any credential I would ever get. In this example, I'm giving it the root Postgres user. And I tell Vault, this is what you're going to use to connect to Postgres. Here's the string. In this case, it's running over localhost. Here's how you connect to it. So I've given Vault the root user. Then, in the next statement here, I tell Vault to create a role named read-only. And I give Vault the raw SQL to execute on my behalf to create that user. So that same SQL that you got from that Stack Overflow post, you can still use that. But now you're putting it in this creation statement. But you'll notice that there's these curly braces here, this curly name and curly password and curly expiration. Vault dynamically generates a username and a password and an expiration time and fills those in for us dynamically. So if you already have stored procedures or functions for creating users, you can still leverage those because this is just raw SQL that's going to get executed against the database. But you parameterize it with these curly braces. And anything in there gets filled in automatically. The last thing you'll notice are these bottom two lines here. Move this up a little bit for folks in the back. These bottom two lines here, this default TTL and max TTL. TTL, or time to live, is that lease, that lifetime of the credential. So remember earlier we were talking about DHCP and how DHCP expires. This is true of these credentials as well. You can see that there's a valid until clause in our SQL, but then we're also specifying these TTLs. This says, hey, this credential is valid for 15 minutes unless you renew it. At the end of 15 minutes, I'm going to delete this credential from Postgres automatically. And at the end of 24 hours, I'm going to delete it even if you're continuing to renew it, because I want forced rotation of credentials. So let's go ahead and run this configure database script. It's very quickly. And now what I'm going to do is I'm going to generate a database credential. Vault read. And just like that, I've generated a database credential. This V token read only and this password, the A1A, those are real Postgres logins for my local Postgres server. That's a real Postgres username and a real Postgres password that can be used to authenticate to this service. If you don't believe me, there it is. It just got created. I promise I didn't make that in advance. If I did, that would be very, very, very random. So this is a real user that Vault generated. And each time I read from that endpoint, I'm going to get a new username and password. So even though they both start with A1A for the password and they both start with vToken read-only, you'll notice that the data after those is different. So each time I read from this endpoint, I'm going to get a new credential. So that means if I have two applications that boot up at the same time, they authenticate to Vault at the same time, they make an HTTP API call to this endpoint, they're going to get a different username and password. And now we have provenance. We have a one-to-one mapping. But most importantly, no human saw that credential. The application is the only thing that has ever seen that credential. Because of that, and because this is programmatic, meaning it can be automated, we can limit the scope of our database credential to just the tables and just the permissions that it needs. It's very common to create kind of the super user because it's really hard to make a database credential and it's hard to make it portable, so you just give it a bunch of permissions and hope no one hacks it. With this, because it's so programmatic, we can actually just make very, very limited scope credentials that just minimum viable product for security. Now what I'm going to do is I'm going to log in as one of those users we created at the beginning. So I'm going to log in as Chris. Chris's password is password. Don't tell anyone. And now what I'm going to do is I'm going to create a database credential as Chris. So you'll notice same API point, same everything. Username and password is a little bit different. It says vuserpass instead of vtoken, because Chris authenticated via the username and password authentication, whereas I was formerly the root user or the root token. And now Chris has authenticated. He has this vuserpass read-only. If we run du, we'll see that this vuserpass read-only is down here at the bottom. That's Chris's credential. If Chris tries to do other things in the system, like access the key value store, he actually gets access denied because Chris does not have permission to access that. We didn't give Chris permission to do that. We only gave Chris permission for Postgres. So there's a really deep ACL system at play here that we don't really have time to jump into. So let me log in as the root user again, and I'm going to generate a bunch of credentials. Basically just simulating kind of a real production environment where you have a bunch of different users and a bunch of different applications that have all requested access to this database. So if we go into Postgres now, and we look at all the users, we can see there's quite a few in there. So what happens if today's Chris's last day at the company? Ideally, all of the database credentials that Chris has generated are no longer valid, because Chris could take those with him or her and access them later, and that could be a leak. How do we revoke just Chris's credentials or just Bobby's credentials because they're no longer with the company? Whether they left on their own accord or whether they got fired, it's still a good best practice to revoke them. So what we can do is we can actually run vault token revoke for all of Chris's logins. And this will revoke all of Chris's credentials. So anything Chris created, any dynamic credentials that Chris created are now revoked automatically. It's going to be hard to see because there's a bunch of other credentials in here, but Chris's credentials are no longer in here. But what if it was worse? What if we had like an Ashley Madison style data breach where we knew we were compromised and we needed to recover as quickly as possible? And it would be better to take downtime than to continue leaking data. We could just revoke all of the database credentials. Like, revoke them all. We know it's going to cause downtime, but that's better than losing data to an attacker or a hacker. Well, with that, we can actually run vault lease revoke everything issued by the database secrets engine. Now, that's a queued operation because it can take a little bit of time, because you can imagine you'd have hundreds of thousands of these. But all of them are gone. So Vault connected to Postgres and revoked all of those credentials early. So anything that was connected to that is no longer connected. Any attacker that was using that credential, it's no longer valid. All right. So the last thing I want to show you before I run out of time is Vault tries to be a single source of secrets. So we're talking about things like encryption as a service and managing database credentials. But how many people here work on a website that offers multi-factor authentication or TOTP? Okay, how many people have ever read the TOTP white paper? Yeah, I have, and then I died. True story. So Vault can actually be a TOTP provider. And this is where Vault really tries to be the central source of secrets. You could delegate multi-factor authentication to something like Vault, the same way you could authenticate it to something like Authy or Duo. So very quickly, I'll show you this. And if you have questions, you can put them in the Slido. I don't know if I'm saying that correctly. So I've enabled this TOTP secrets engine. I'm going to quickly create a key named Seth. I'm going to ask Vault to generate it. I'm going to say the issuer is build stuff, and my account name is my email. Please don't spam me. And I get back two pieces of information. I get back this OTP auth URL and this thing way up here, which is called barcode. That's actually a base64 encoded PNG. So if I echo that, pipe it to base64 to code, and then save that as a PNG, and then open that. Look at that. It's a PNG. That looks familiar, right? How many people have seen one of those before? Then if I come over here, and this is not an endorsement for 1Password, but you probably should use it, and I scan this over here, I get multi-factor authentication. Same way you would get with something like Google Authenticator or Authy or Duo. I'm going to wait 2 seconds. OK. Now I come back here. I copy that to my clipboard. I ask Vault to verify the Seth code, and it comes back as true. Last thing I'll do is prove to you that if I change it, it comes back as false. There's no questions. That's all I have. That's a lie. There's one more slide. That's all I have. But I'm happy to take questions now or the rest of the conference. Thank you. You can also just ask questions, and I'll repeat them. Yeah. So the question is, how do you actually store the credentials for logging onto Vault? It depends on how you want to authenticate. So let me just pull up a browser very quickly. So Vault has these things called auth methods, which are pluggable, so you can write your own. But there's a bunch of built-in ones. Auth methods. So here's all of the built-in ones. I'll make this a little bit bigger. So you have app role, cloud provider specific ones. So Ollie Cloud, AWS, Azure, Google Cloud, Kubernetes to a certain extent. In those examples, you can trust like cloud metadata. So you actually don't have to store credentials anywhere. You delegate authentication to like the Google Cloud Metadata API or the AWS Metadata API. In the case you're running on like on-premise or you can't trust the cloud provider for whatever reason, you can do things like LDAP, Okta, Radius. Those tend to be oriented towards humans. And then there's machine-based authentication, things like JOT tokens or app role, where you can bake credentials using your configuration management, like Chef, Puppet, Ansible, Salt, and then provide some type of runtime secret at application boot, which can then be validated together as a piece of information to get the initial credential. Does that answer your question? And they're pluggable, too. So if you have some crazy internal auth system, you can write your own plugin. Other questions? So the question is, how do applications deal with the fact that their credentials expire? There's a few ways you can handle this. If you're building an application from scratch, generally you want to make sure that it responds to some type of reload signal. And then you can use some sidecar template. If you're using like Kubernetes, a sidecar container that sends a signal when that time expires. There's also an open source project called Console Template. GitHub /HashiCorp/console template. That, which does that whole process for you. And it writes the credentials out into a template on disk. So this allows you to pull data from like multiple Vault sources. You might have like 3 database credentials, a Redis password, and a Google service account, and you put them all in the same template file. So your application just reads a template. It's actually totally unaware of Vault, and then it responds to a signal or some Unix socket that like, hey, this thing has changed, and then it reloads its config or whatever happens to the application layer. If you're running on something legacy, like some real old school COBOL or Java application, it's actually really hard. Particularly when you're dealing with Java, because the startup times are so slow. If you do like a hard reboot or a hard restart of the application, you could be dealing with 5 to 10 minutes of downtime. There's no real good pattern for that. Some people have come up with things like they'll spin up a new instance and do load balancing at that layer, but there isn't a really good established pattern for legacy apps right now. Yep. Other questions? There's still none down here. Yeah. What's that? I don't have any down here. Am I doing it wrong? I'm just going to refresh this. Yeah, I don't have any questions on here. How do you know if the service is? Can you just speak up just a little bit? Sorry, the fans up here are really hard to hear. So the question is, if I log into Vault, how do I get authorized to get credentials from Postgres or MySQL or whatever. So there's an ACL system, an ACL system in Vault that we didn't have time to dig into. There's a policy engine. So you write a policy, and you say that this user or this group has access to these things. So let's take GitHub as an example, or LDAP. Users authenticate via GitHub or LDAP. Then the security team or the Vault administrators basically create a policy that says, anyone in the GitHub team developers or anyone in the LDAP OU developers has access to these 15 resources. And then when the users authenticate, they inherit those policies. Other questions? OK, well, I will be around the rest of the conference. If you have questions that you didn't feel comfortable asking, you can ask me later, or my DMs are open on Twitter. So feel free to reach out. Thank you all for coming. Enjoy the rest of the conference.